In 1913, a clerk in the Madras Port Trust earning £20 a year sat down and wrote a letter to the most important mathematician in England. The letter was 9 pages long. It contained 120 theorems. No proofs. No formal derivations. Just results, written out in neat handwriting, as if the answers were obvious and the proofs were someone else's problem. Some of the results were already known. Some of them were wrong. And some of them were so extraordinary that the greatest number theorist alive would later say they must be true, because nobody would have the imagination to invent them. This is the story of Srinivasa Ramanujan, the man who dreamed in equations and left behind notebooks that mathematicians have been trying to understand for over 100 years. Ramanujan was born on the 22nd of December, 1887, in Erode, southern India. His family was Brahmin but poor. His father was a clerk in a sari shop. By the age of 12, he had mastered a borrowed textbook on advanced trigonometry, a book meant for much older students. He was 12. At 15, he got hold of a copy of Carr's synopsis of elementary results in pure and applied mathematics. This was not a great book. It was a dry compendium of 5,000 theorems stated without proof, originally compiled as a coaching manual for Cambridge exams. Most students would use it as a reference. Ramanujan treated it as a starting point. He began filling notebooks with his own results, working alone, without teachers, without guidance, and without any knowledge of what European mathematicians had been doing for the previous 2 centuries. He was reinventing mathematics from scratch. And in several cases, surpassing it. He failed his university exams twice, because he could not be bothered with any subject that was not mathematics. He lost his scholarship. But the notebooks kept growing. The notebooks are extraordinary. There are 3 of them, written between roughly 1903 and 1914, plus a collection of loose pages found after his death, now called the Lost Notebook. Together they contain approximately 3,300 results. Most have no proofs. Just statements. Ramanujan would write down a continued fraction identity, or a bizarre infinite series, or a transformation formula, and move on to the next one. Many turned out to be correct. Some anticipated discoveries that would not be made by anyone else for 30, 50, or 80 years. And a handful remain unproven to this day, verified computationally to billions of cases but never formally demonstrated. The notebooks do not read like mathematics. They read like prophecy. As if Ramanujan could see the answers directly, without needing the machinery that connects the questions to the solutions. The mathematician Bruce Berndt spent decades editing them. He described the experience as opening a box and finding treasures on every page. On the 16th of January, 1913, Ramanujan posted a letter to G. H. Hardy at Trinity College, Cambridge. Hardy was the leading pure mathematician in Britain, famous for his rigor and his contempt for sloppy reasoning. He was not the sort of man who suffered fools. Ramanujan's letter opened with a polite introduction. Then came 9 pages of results. No proofs. No methodology. Just formulas. Hardy's first instinct was to dismiss it. He received letters from cranks regularly, and most of them were obvious nonsense. But something in this letter stopped him. He showed it to his colleague Littlewood. They spent the evening working through the theorems one by one. Some they recognized as known results, which was a good sign, because a fraud would not bother with known truths. Some they could prove were correct. And some they could not prove at all. Either the theorems were wrong, or the man who wrote them was a mathematician of the highest order. Hardy later said that the theorems defeated him completely. He had never seen anything like them. They must be true, he concluded, because if they weren't, no one would have the imagination to invent them. In March of 1914, Ramanujan boarded a ship to England. He was a strict vegetarian Brahmin arriving in a cold, grey, rationed, meat-eating country in the middle of the First World War. He struggled with the food. He struggled with the weather. He struggled with the loneliness and the complete absence of everything familiar. He cooked his own meals in his rooms, sometimes going days without proper nutrition because the ingredients he needed were not available in wartime England. But mathematically, the partnership with Hardy was electric. Hardy provided rigor and formal technique. Ramanujan provided vision. They were opposites in every respect, and together they produced some of the most remarkable results in the history of number theory. Hardy once said that his greatest contribution to mathematics was the discovery of Ramanujan. He meant it as a compliment. It was also an act of humility from the most arrogant mathematician in England. On the scale Hardy invented to rank mathematical talent, he gave himself 25. He gave Littlewood 30. He gave Hilbert 80. He gave Ramanujan 100. The most celebrated result of the Hardy-Ramanujan collaboration concerns the partition function. A partition of a number is simply a way of writing it as a sum of positive whole numbers. The number 4 has 5 partitions. 4 itself. 3 plus 1. 2 plus 2. 2 plus 1 plus 1. 1 plus 1 plus 1 plus 1. Simple enough. But the partition function grows with terrifying speed. The number 10 has 42 partitions. 20 has 627. And 200? Roughly 3,972,000,000,000. There is no simple formula for this growth. The numbers explode. Hardy and Ramanujan found an asymptotic formula that approximates the partition count of any integer. It uses pi. It uses square roots. It uses exponentials. It converges with extraordinary speed. The result was published in 1918 and remains one of the great achievements of analytic number theory. Later, Ramanujan refined their approach into an exact formula. But the flash of insight, the connection between partitions and the circle method, was Ramanujan's. Hardy provided the proof. Ramanujan had already seen the answer. One of the most famous stories about Ramanujan has nothing to do with a proof. Hardy went to visit him in hospital in Putney, where Ramanujan had been admitted in poor health. Hardy mentioned that his taxi had been number 1729, which seemed rather dull. Ramanujan disagreed immediately. 1729, he said, is actually very interesting. It is the smallest number expressible as the sum of 2 cubes in 2 different ways. 12 cubed plus 1 cubed. 10 cubed plus 9 cubed. Both equal 1729. Hardy asked whether Ramanujan had known this before or worked it out on the spot. Nobody is entirely sure. Ramanujan may have encountered this number in his own work and simply remembered it. Or he may have seen it immediately, the way some people see color or hear pitch. Either explanation is remarkable. The number is now called the Hardy-Ramanujan number. The general problem of finding such numbers is known as the taxicab problem. It remains one of the most charming anecdotes in mathematics. Also one of the most unsettling. Because it suggests a relationship with numbers that is not learned but innate. Ramanujan had an almost supernatural instinct for infinite series. He discovered formulas for pi that converge at speeds no one had imagined possible. His most famous pi series gains roughly 8 decimal digits per term. To put that in context, most classical series for pi gain about 1 digit per several 100,000 terms. Ramanujan's formula was so efficient that it formed the basis of the algorithm used by the Chudnovsky brothers in 1989 to compute pi to over 1 billion decimal places. He also produced identities involving continued fractions that are so baroque, so structurally unexpected, that mathematicians spent decades trying to verify them. The proofs exist now. But Ramanujan did not need them. He wrote down the identities and moved on. As if the proofs were, frankly, beneath him. In January of 1920, 3 months before his death, Ramanujan wrote a final letter to Hardy from Madras. He was gravely ill and he knew he was dying. The letter described a new class of functions he called mocktheta functions. He gave 17 examples. Hardy was fascinated but baffled. He could not fit these functions into any known framework. Nobody could. For 80 years. The mocktheta functions sat in the literature as beautiful orphans, clearly important, but belonging to no established theory. Then, in 2002, Sander Zweigers, a Dutch doctoral student, finally cracked the problem. He showed that the mocktheta functions were pieces of harmonic Moss forms, a generalization of modular forms, which are among the deepest structures in modern number theory. Ramanujan had glimpsed, in his final weeks of life, a mathematical structure so advanced that the rest of the world needed 82 years and entirely new branches of mathematics to understand it. Mocktheta functions now appear in string theory, black hole physics, and combinatorics. Ramanujan could not have known any of this. He simply saw that the functions were important and wrote them down before he died. Ramanujan died on the 26th of April, 1920. He was 32 years old. He had spent 5 years in England, returned to India in failing health, and never recovered. The cause was likely hepatic amoebiasis, a parasitic liver infection exacerbated by malnutrition and the English climate. In his 32 years, he produced roughly 3,300 results. His lost notebook was rediscovered in the Wren Library at Trinity College in 1976, more than 50 years after his death, sitting in a box of papers that had been largely ignored. It contained 600 results. Many were new. Some still have no proof. It was as if Ramanujan had left behind a time capsule addressed to mathematicians who did not yet exist. Here is what makes Ramanujan genuinely unsettling. He was almost always right. His methods, insofar as anyone can reconstruct them, were not methods in any recognizable sense. He did not build proof step by step. He described his insights as coming to him in dreams, placed there by the goddess Namagiri. Hardy, the ultimate rationalist, found this explanation deeply uncomfortable but could not dispute the results. The formulas worked. The identities held. To this day, we do not fully understand how Ramanujan worked. His intuition operated in a space that formal mathematics has not yet fully mapped. There are conjectures in his notebooks that have been verified computationally to billions of cases but have never been proven. The results are almost certainly true. We just cannot explain why. The proofs, if they exist, may require mathematics that has not been invented yet. We are still catching up to a man who died over 100 years ago. Srinivasa Ramanujan had no formal training past secondary school. No degree. No teachers. No community. He worked alone in a small house in Kumbakonam, filling notebooks with mathematics that the rest of the world had not yet invented. He sent a letter to a stranger in Cambridge, endured 5 miserable English winters, and reshaped number theory. Then he went home and died at 32. 100 years later, mathematicians still open his notebooks and find results they cannot prove. The Fields Medal citation for Manjul Bhargava in 2014 referenced Ramanujan's work. His fingerprints are everywhere in modern mathematics, left there by a man who never learned the formal language. There is no clean moral to this story. There is only the strange, uncomfortable fact that genius does not wait for permission, or preparation, or even survival.